So this is section 9.2, the second section of chapter 9, Introduction to Soil Structure Interaction. First part was Introduction to Ground Response Analysis. So this part focuses on SSI, which follows basically the ground response analysis. So ground response analysis, we saw it using the wave propagation techniques, or it can be done also, full-time history analysis, but it mainly focuses on the soil part. But now if you are introducing some structure on it, any kind of structure, can be buried structure like tunnels or dams or buildings, anything, then that's going to be SSI, soil structure interaction. So SSI is when we have one single structure. But if you have multiple structures sitting next to each other, we call it also triple SI, structure, soil, structure, interaction. So there would be something like you have a ground surface, let's say you have one structure here and another structure here. You have a soil. So this is when you have, because the free field, the response of the soil without a structure, it's different from when you have a structure on it, because the structure affects the soil response, and the soil affects the structure response. Now, when you have a second structure very, very close to it, even the presence of the other structure affects the response of the nearby structure. So that's when you call it SSI. And you may have several buildings next to each other. Usually, if you have a very massive structure, let's say this is very massive, very big, and you have a small structure here, the impact of the big one on the small one is significant. Let's say you may get response spectrum at every floor, some accelerations, bending moment, shift force, anything for the small structure without the big structure around. And if you run the simulation again with the big structure nearby, there would be significant change in those responses. So usually a big structure affects a small structure significantly. But a small structure doesn't affect significantly a big structure. And it depends also how far it is. If it's very far away, probably there is damping and the motion is not that much impacted by the presence of those two structures. So that was the part you asked me. So if you have structures next to each other, there will be impact on each other. In my observation in the past, a massive big structure next to a small structure, the small structure should consider the effect of the larger structure because there will be a big change. But when you analyze the big structure, you can ignore the small structure. The impact is negligible. So there are papers discussing these simulations. You can do modeling like SASI can do this. A big structure approximately can model it and a small structure nearby. So you can get a direct output, a direct response or impact on the small structure. Other softwares also can do it, but the more you increase the number of structures, there will be limitation how much you can do. So that triple SI structures for structure interaction, that's the area what it covers. Impact of other structures on nearby structure. But when you have one single structure, that's what we call usually SSI, soil structure interaction. So traditional structural geotechnical engineering methods disregard SSI effect. For example, a structural engineer assuming a fixed base and analyzing a structure, it's not accounting the impact of soil. There is some soil flexibility. So remember that kinematic impact, inertial impact is above ground from the structure. Kinematic impact is from the soil. So when you assume a fixed base analysis, it's usually ignoring the kinematic portion. So it's acceptable only for light structures on relatively stiff soil or rock. Any structure on strong bedrock, something like shear wave velocity is greater than 1500 or 1500 meters per second. This is very stiff rock. If that's the case, rigid assumption is not bad. But if the rock is like a sedimentary rock, much lower shear wave velocity, it has flexibility, the impact is significant. For structure sitting on soil, soil structure interaction analysis or site response analysis needs to be performed to include soil impact. That's what it means. If you have, like, I gave you this example several times. Let's say you have a rock, outcrop rock, and bedrock. So on the outcrop part, if this is like stiff rock, something larger than 5,000 foot per second, for nuclear power plant design, we are allowed to use fixed base analysis. That's US NRC, Nuclear Regulatory Commission. It allows us to use fixed base if the shear wave velocity within a rock is much, much larger, something like this. Anything less than this, we have to account the rock. For soil, it's usually much less. And you have to do SSI. You have to include the model of the soil together with the structure. So when we design, when we analyze nuclear power plants, we put the nuclear power plant on the soil. There may be some embedment, and then we include the impact of the soil. We go deeper, like 300 foot, 500 foot, to include the soil in the model. So that was a software I call the SSI. That's what it does. Include a soil model, a structure model together, and apply input motion. So you are accounting the flexibility of the soil. SSI is required because foundation can have relative displacement, can slide with the shear force from seismic, or it can rotate the ground and affect the structural response. So your foundation can move, can try to rotate, or it can slide. If you fix it in the analysis, you're losing all this. Advantage of considering SSI. So there are, depending on the soil, the rock, there are some advantages by considering SSI. If you see, when you consider SSI, it's getting more flexible. It's allowing you to move. When it's rigid, it's fixed, it's not moving. So if you see it in the input motion case, for example, you have a time history like this. You convert it into response spectrum. From response spectrum, now like in a pseudostatic design case, you get fundamental period of your structure, you pick the corresponding acceleration, and you can use that in a simplified version. And we say to account for higher modes, you can multiply those 1.5. And even if you are in the higher, in the rigid zone case, this is a high period, or in this case, then it's very low. You can even get flatter. What does SSI doing is, let's say you have this response spectrum. Let's say you have a building with this fundamental period, let's say 0.5 second. When you account for the flexibility of the soil, so the whole structure is getting flexible. Let's assume exaggerated case. If it's flexible, is it going to be high period or low period? Remember those Mexico City buildings, the tall buildings, they didn't get suffer, right? They stand still, maybe with minor cracks, window cracks, something minor. The shorter one, the stiffer ones, they were badly hurt. So the stiff ones, it's getting low period. If something is rigid, it has low period. Remember, the zero period is the ground itself. That's rigid. If it gets flexible, it's going to be high period. Right? So by introducing flexibility in the soil, we are making the whole model more flexible. If it's flexible, it go away from the peak zone. What's happening is it can go away from the peak spectral acceleration case. A building which is designed with fixed base at around 0.5. Second, by accounting flexibility of the soil or rock it has, we can increase it to the entire system to have, let's say, 2 seconds. Let's say it moved from 0.5 to 2 seconds. So what's the impact now? Is it better to design this at a 2 second fundamental period, or is it better to design a 0.5 second fundamental period? Anumut, I promised you to ask you a question, right? Which is better? Is it better to design a building, at least for this response spectra plot? Is it better to design a building with 2-second fundamental period, or is it around 0.5 second? 0.5 will give you around this much, let's say 0.9 g spectral acceleration. But with 2 second, you're designing it around 0.25 g spectral acceleration. Which one will give you larger force on the building? 0.9 g or 0.25 g? Yes, 0.9 will have a significant impact on the structure. So we should design it much larger reinforcement, much larger sections for our framing system. Walls, beam, columns, slabs, anything. But if you design it with 2 second fundamental period, the seismic force acting on it, it's too small. So, which means by introducing flexibility of the soil, by not fixing it, we are doing economical design. Is that clear? So SSI, actually, it can help. Less seismic forces act because you're allowing it to move. When the force acting on a building, if there is flexibility, it moves a little bit. If it moves a little bit, it's doing some work. So the stresses, bending moment, anything acting on the members, it gets less. So the more flexible, the better. Another advantage of considering SSI is that it increases effective damping ratio of the system. If you're fixing it, we're not considering damping, right? We are introducing high energy. Whatever input we apply on the structure, it's going in the structure and then going back, reflecting back. That's bad. There is nothing absorbing what's coming, the energy that goes in, the wave, when it comes out, it should come out. Otherwise, you have high energy trapped within the structure if you analyze as a fixed base without damping. So when you introduce a flexibility of the rock, then you're also assuming to have some kind of damping. It absorbs the energy, so less motion. So you have these two advantages by considering SSI. But doing SSI is not easy also. That's the penalty. I mean, fixed base is easier. You ignore the soil and do a fixed base run. But when you're doing SSI, now you have to include, get the properties of the soil, either model it as springs with dampers, or you can use like a wave propagation technique like SSI and other software so that you can include the soil itself. So you'll have more work to include the impact of the soil. And the other thing, actually, Nuclear Regulatory Commission, they force us because in case if there is a resonance in the soil, you can only see it. That resonance, that amplification being introduced into the structure. Sometimes what people do is they analyze the soil alone and use that output right here and try to use it for the structure. No. You can do that kind of approximation, but it's not realistic. Because when you do the wave propagation through the soil, the impact of the structure will affect how much output you'll get at the ground surface. So NRs usually force us to do it together. Everything together. The soil and the structure together. So that's how commonly it is done for critical structures. Something like my experience is in the nuclear industry, designing nuclear power plants worldwide. That's why I say so many times nuclear power plant, nuclear power plant. But other critical structures like dam and high-rise buildings, you can also do the same. Degree of influence of SSI. The degree of influence of SSI on the response of structure depend on factors like the stiffness of the soil. Soft soil have different response from a stiff soil. dynamic characteristics of structure itself, natural period, and damping factors, and the stiffness and mass of the structure itself. Sometimes when you analyze a structure, you may observe a phenomena like resonance. Let's say you have a soil, and let's say when you do your SSI, you get significant output on some floors. The acceleration level at each floor or the response spectra we develop at each floor, which help us to design the framing system in that location, they may be significantly high. And you may have a resonance where the soil is resonating with the earthquake and creating a resonance in the structure. So if the structural fundamental frequencies are close to the soil and the input, that's when you get your amplified motion. In those cases, you may be forced to modify the structure. If you simply see it, period of or fundamental frequency of a structure is 1 over 2 pi square root of k by m, right? Just assume it as a 1 degree of freedom system formula. If the fundamental frequency is getting close to the soil, you know how to estimate the fundamental frequency of soil, right? Or a period, Vs by 4h. If the two get close, then it's hard to modify the soil, but you can modify the structure. You can get maybe one technique maybe to reduce fundamental frequency or increase period. To increase period, what you can do? You can play with the mass of the structure. If I increase the mass, what happens? Let's say I increase the mass by a factor of 2 or 3. Let's say in a short one-story building, I added a water tank on top of it. That increases the mass, right? But that increasing the mass, what it does is the mass is increased, let's say 2 times, then the frequency is what's happening there. The frequency decrease because it's k by m. But the period increase, the reverse. So you can modify like that. If you see it's getting close to the resonance or high acceleration area, you can play with m, the mass, like a water tank, simple example. Or you can play with k. K is what? The complex stiffness of the structure, beams, column, slab. Those you can play with those and increase or decrease k, stiffness. If you play with any of them with m over k, you can shift the frequency. The idea is called shifting the frequency to get out of that peak area, this area. You can artificially shift away from this area by playing with k and m. So that those are the concepts being used. Avoiding resonance between soil and structure is a critical aspect of design. Resonance occurs if a natural period or fundamental frequency of soil closely matches with natural period of the structure. SSI has positive impact only if the structure is designed not to have resonance. If you avoid resonance, then SSI is advantageous. You're introducing damping by considering some observation in the base, and you are moving it also, you are adding flexibility. Ground response analysis can provide more realistic fundamental frequency of complex layer of soil. For uniform layer, the soil fundamental frequency can be estimated, right? These are the equations we derived in the previous slides under the section 9.1. So for the soil, you can use this roughly to estimate. If you have several layers, VS can be a weighted average just for a quick estimation. And for the fundamental frequency of the structure, usually structural engineers, they do something called modal analysis. Modal analysis is something before you do like a time history or spectral analysis. Something modal is so quick, but it is give you the fundamental modes of the structure. So you compare the two, the soil and the structure, and see where you are. So this is exactly the Mexico City phenomena. You're trying to avoid resonance. So in Mexico City in 1985, we have seen this example so many times, but we can repeat it here. What happened there is certain buildings with stories from 5 to 15, they were resonating with the soil. The soil was having 80 meter per second average wave velocity, that's soft clay deposit. And if you consider average depth of 40 meter, fundamental frequency for the soil was Vs by 4H, around 0.5 hertz, and the period, fundamental period was around 2 seconds. So those structures closely matching with 2 seconds in fundamental frequency, they were severely damaged, especially buildings in general from 5 to 12 stories, 5 to 15 stories. And there was huge amplification in the motion because of resonance, anywhere between 5 to 12 times of the rock motion. So that's what we have seen this. This was what's expected, the magenta line 1985. This was what the code requirement was. This dash line was what was recorded at the rock point. Rock is this one. If they were designing it for the rock, they are okay. It's enveloped. But the soil amplified is so much from here to here. Significantly large acceleration acting on the structures. And that's why there was like so many catastrophic damages in those buildings. We have seen it in chapter 1 and I think chapter 2 also, those case histories documented resonance failure. So you can go back and look at it, or you can get more information, I think, from this link. So there was about 12 times amplification. SSI methods, two most common approaches in SSI are direct method, direct integration. We have a general dynamic equation, the inertial component, if you remember from chapter 2, theory of vibration. Inertial component, the damping component, and the stiffness component. And this is the ground motion, the forcing component. So there are methods using directly integrating this in the soil and in the structure. Or the other method is substructuring method. This is more simplified and it's much quicker. In the direct approach, if you integrate this in the soil, it's like, usually it's done in time domain. And it's so time taking. The solution is usually in time domain and it can take significant amount of time for complex problems, large meshing, so many large number of finite elements, which makes this have limited application for practical case. The quality of the solution depends on several factors such as finite element mesh size, time step you're using for the solution, and the quality of the constitutive models. One big advantage of this method is full nonlinear of soil and can model for water pressure during seismic liquefaction. This is the same method implemented something like in Plaxis, FLAC, even if they are mainly used for geotechnical part, but they do it in time domain. So you can have your soil part and the structure part. You can generate the mesh, introduce the input, and you're solving this dynamic equation at every time step. That's why it's called the direct method. In direct method, motion is applied at all boundaries. If this is a surface, you have your input all around. And the general dynamic equation of motion is solved at small time step, which makes computational intense. Example of direct method, Yubek Alcazar's thesis work, he used Flax 3D, and that's what he did, using direct method. So he has limitation how much the model should be, and it's time taking. As the model size increases, it's very time taking. He has limitation how much detail he can go in the structure. FLAC at least has a capability. Now, when I know FLAC, it didn't have structural elements. Now it's introducing structural elements, beams, columns, even foundations. So he was able to model and run the simulation, and because it's a direct method, he was able to do liquefaction modeling within the soil. This is what he get for liquefaction. Dynamic time, excess pore water pressure. You remember this plot? You can get similar plot from shake table and centrifuge, we have seen it. Or you can use softwares to do this. The pore water pressure getting around 1 and going down. Liquefaction happened right away. There may be some limitation in the simulation. Usually it grows slowly and reaches 1. But he was able to get something. In forces, drift, shear forces, bending moments in the structure and in the foundation elements. So you can look at the thesis he did and what he accomplished. And I'll talk to him at the end of this class so that he can introduce you with flag so you can play around. And flag is widely used for geotechnical engineering for other purposes. Here it's being used for dynamic analysis, but you'll see flag for wide application for dams, slope stability, and other geotechnical problems. It's well-known commercial software. The other method for SSI, substructure method. In substructuring method, the total structure is subdivided and solved separately, allowing different solution techniques for different parts. Wave equations, that's where wave equation come, is much convenient for the soil free field portion and finite element for the structure portion. So what's done is, the structure is we're using finite element method. But for the soil part, we're using solution from the wave equation. We can see the propagation of the wave by solving directly the wave equations. It's much faster rather than doing finite element and then see how the wave propagate through numerical methods. So there are the structure in the soil, they interact at some nodes. This may be a basement floor, excavated soil, and there would be along the boundary at the interface point, you have these nodes. So the output from the structure, the output from the soil, they interact at the interaction nodes. So that's the main idea for substructure method. So like, for example, if this is excavated soil, to put the structure, what it does is you have the free field motion, but from there, you reduce the excavated soil. And then you add the structure. So what you get from the wave propagation at the interaction points, they will be input to the structure. You solve the structure, then it comes back, provide input to the soil. So they are alternatively working. So we're combining different techniques. Finite element here is much better. For the wave propagation is much better. If you use finite element in all three cases or finite difference, it's computationally expensive. There will be some limitation. In most common case, the soil free field can be solved using wave equations. That's done in frequency domain. And the structure foundation using the general dynamic equation of motion. That's a finite element method. This method is computationally more efficient than the direct method, as most of the disadvantage of the direct method can be removed and large complex problems can be solved. This method uses solution of wave equations for soil and does not need a special quantity model for soil part. So for complex SSI problems such as nuclear power plants, in my experience, we use that SSI software, which is a combination of this finite element and solving the wave propagation equations. So this is a summary of comparing the direct method and the substructure method for comparison of direct and substructure SSI methods. So in the direct method, need fine mesh, because this is finite difference method, especially for flag, you have to mesh the soil here, both horizontally and vertically. And wherever you are stopping the model, you have to introduce for some damping here, horizontal, vertical, here also. Yeah, at some point in the depths, like if you have bedrock, you may introduce some springs with dampers, or somehow you should introduce damping for dynamic case. so that the waves also entering should be living. Substructure method, it need only horizontal soil layers. No vertical mesh required, can go to large depths. So what this is all you need for the wave propagation. Remember what we have, impedance ratio. So all it does is we need just horizontal layers. And this is infinity, the model goes to infinity. You don't need like a vertical mesh and elements like it. You don't need specific elements. All you need is layers. So the model goes up to infinity. All you introduce is just a horizontal mesh, that's it. Because of this, the wave equation is much faster to solve it here. You can go much deeper depths here. This may be limited to be 20 meters. This can go up to 100 to 100 meters. Wherever you find good stratum like rock. But even then, you introduce your damping, even if I'm not showing it at the base here. It's not fixed base. Need lateral soil boundary. Here you need your boundary. Call it free field boundary and with some dampers. Here you don't need free field boundary. It's infinity. Infinity lateral soil. No lateral boundary required. Time domain is used in the solution. Small delta T needed. About 10 raised minus 6. Makes solution slow for complex problem. Practically limited application. But here it's frequency domain. Need important modes only. The beauty of using frequency domain, you solve the equations only at some selected frequencies. Those selected frequencies, you can select it based on the fundamental mode of vibration. Where is the first mode? Where is the second mode? Where is the third mode? Wherever the peak modes are, you select more frequencies to capture the peak. In other locations, you don't need that much frequency. And at the end, for nuclear power plant, I've been using around 60 frequencies. So 60 solutions only. 60, 70, 80. And we use interpolation for the interior points. But in time domain, you're not allowed to do that. You should go from 0 to 20 or 30 seconds, depending on the duration of the seismic motion, at every small time step, like 10 raised minus 6. So it's slow. In direct method, you can use nonlinear soil. Have a capability of linear soil also, but you can use nonlinear soil. But in substructure method, it's equivalent linear soil. What is equivalent linear soil? Get to. What did we discuss before? How we get that? Fully nonlinear and equivalent linear. What's the difference? وبشكل yeah, it's something like, constitutive models. That we are capturing the full high stress loop, the tangent for the high stress loop at any point. But when you say equivalent linear, it's the second modulus, the average for high stress loop. And equivalent linear, so those degradation curves we developed from the second modulus, which one is this? Is that the linear or equivalent linear? Equivalent linear. The GG-max degradation curves, the damping curves we developed in chapter 5, they come under this equivalent linear. They are being used for shake and for SASI analysis, that's the input. But if you are using constitutive models to get a full nonlinear behavior, like a fin model in FLAC. So even if too slow, you have a better nonlinearity approach. But this is like approximate for a high stress slope. We use one G value, average for high stress slope. So the direct method, it can model pore water pressure increase because you have those constitutive models. But in the substructure method, it doesn't do that. At least so far. When we developed those constitutive degradation curves, we didn't talk about water pressure increase, did we? No, we didn't. So that's one limitation. It's faster to get the structural response, but it has a limitation, water pressure increase, say something to predict liquefaction. That can be done in something like FLAG. Or liquefaction evaluation, the one we saw yesterday in chapter 8, you can do it outside. Get the factor of safety against liquefaction, and you can predict if the soil is liquefied or not. If it's going to liquefy, then you can introduce some mitigation before you design your structure. Example substructure SSI analysis of nonlinear nuclear power plant using SSI. So you can have a complex nuclear power plant structure. This is just a random example from SSI manual. I'm not allowed to show you any example I did in the past because of security reasons. But this is, you can find this from SSI manual. It's a lot complicated structure, and you don't see the soil here actually. You can have the soil, it's model much deeper. Doesn't visualize the soil model here, but you expect the soil together with the structure. This is thousands of finite elements and nodes. It's complex. So for SSI, in SSI it takes, depending on the computer you have, high computing power computers, they can solve it maybe. It can take a few days. In my time, it used to take at least a month sometimes to solve it for those frequencies, 60, 70 frequencies. And we solve it for different soils. The soil itself is not one constant. We use average soil property, upper bound and lower bound, at least 3 soil parameters. So the simulation is too much. It takes months to get the whole response at the end. Once you get the response, then you have the seismic stresses for design at every point in the structure. So the structural engineer design those. So doing SSI, it can get really complicated. Doing this in FLAG, it's impossible. Because the limitation in the soil modeling, in the finite element size, finite difference size, and how much it can do. And also, I don't know how well FLAG can do the structure if it gets too complicated. You can model, simplified structure, but not so much nodes. This is probably 100,000 elements and nodes. Dalgidus soil depths can be modeled, something greater than 200 meters. No lateral boundary limits required because it's infinity. Large complex structural models with fine mesh can be modeled. The seismic SSI analysis of most nuclear power plants worldwide are performed using computer programs such as SSI. This specifically because it's a very advanced software. It's developed initially in Berkeley, US Berkeley, University of California in Berkeley, and you'll find it in many consultants, design offices, which are specifically designing nuclear power plants because the regulation requires that. So main reference for this section, it was reference 1, the Kramer book, chapter 7, and a lot of online resources. So you will have some mini project for this section. 10% way due in 2 weeks. Get ProCheck or deep soil, free program and perform ground response analysis for soil deposit with at least 10 meter deep and 15 layers. Use any input motion at bedrock and reasonable soil properties. Perform analysis for both linear and equivalent linear soil properties, constant G and damping values, or some degradation curve you can assume. Teamwork is acceptable, but the final submission should be unique. You can study the program together. So I hope if you do this wave propagation, using these programs. Last year, it was easy for the students to use ProCheck. Those websites I mentioned before, you can get ProCheck from there. And there is a user manual, it's easy. And if you use ProCheck, it can go up to 17 layers, but I'm asking only 15 layers. And just get familiar to it. And I will ask Ivekal to give you introduction on FLAG and just play with it to get some idea of SSI. That completes the course and this chapter.